As a starting point with acid-base reactions, we should mention some things. We do have a K that goes with the action of being an acid or a base. And here's my little fictional anion. We just call it A. It's just some stand-in for whatever anion you care to talk about. But sometimes they actually do this on the multiple choice questions. And it has an H to give. And so here it gave it away. And so it acted as an acid. And so we call its K value for this reaction Ka, and this is a weak acid. That's why it can set up an equilibrium here. A strong acid wouldn't have any ability really to come back left. So this is a weak acid, and if you give it some of this will come back, and eventually you'll hit an equilibrium where the right reaction equals the pace of the left reaction, and that's an equilibrium. So here's our A minus in water, and it's going to act as a base. So we're going to call it Kb for the action of setting up an equilibrium here. And it picks up an H off of water and forms HA. Now it leaves OH minus. And then my point is that let's not write it as just H plus over here, because then we have nothing here. If you write it just as H plus, which I have done and gotten myself really confused with, you just end up with HA, and then you don't know how to find the pH of the resulting system because you have no H plus or OH minus at the end to do your calculations on. So let's not just pick up an H plus. Let's pick our H plus up off of water and form OH minus. Well, then a kid says, no, 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 that's not what would happen. It would pick it up off of H3O plus because you said H plus is really hydronium, so I'm going to write out this. Okay, except I have a further point. Let's write that out and say that it did that. So it picked up, let's say 5A minuses picked up the third H off hydronium and formed 5 HAs and 5 waters. But what happens to those 5 waters is that they now have further room to dissociate in water because remember, Kw must be maintained at this temperature. And you just reduced the H plus molarity in water because this essentially is H plus, right? You just reduced the H plus molarity, so something must fill the gap because Kw must be maintained. It is a law of nature and God on high, or however you want to put it. K will be achieved. How will it be achieved? Those 5 waters will now have a very good chance of meeting up with 5 other waters and forming 5 H3O pluses, which only replaces these that you had originally, and 5 additional new 5 OH minuses. So you can say that that's happening, and technically that is the truth, but it goes the long way around the barn to get to just writing it out like this, and this way I am able to get my OH minus molarity and do my pH calculations. Also, I said Kw must be maintained, but further, there is the point that Ka times Kb equals Kw. So I think it's example 4, we'll see that we're handed one of these, but we actually need the other one. We know Ka, but we're going to have to use the conjugate base as a base. So what we're going to need is Kb for that chemical, not the Ka. Can I find it? I simply take Kw at that temperature, but these are always at 25 degrees Celsius, and it's always a 1e negative 14 for Kw. And I divide it by the Ka that I was told previously, and that will give me the Kb I need for that calculation. So notice these reactions are the reverse of each other, and therefore the K values are the inverse of each other. So if you know one and you realize you're going to have to use the other version, you can take the inverse of the value given. If they give you Ka and you realize, yeah, but I need this to react as a base, you can write it out like this, and you know Kb because it's the inverse of Ka, and that will come up. And they do expect that you know that. Well, we can start off with some more simple problems, and we can use a strong acid like our total classic hydrochloric acid here. And if we put some in, we know that it completely dissociates because we memorized that it's a strong acid and it all separates just upon hitting water. So if I put in this molarity of the acid, and starting even with no product, I get all of it used up in the dissociation, creating this. So then what do I ask for? What am I asked for? pH, POH, percent ionization. The pH is the negative log of the H plus concentration, which I don't even have to do any math for. It's just handed to me. Bam, there it is. So negative log of that. Of course, they do think you can do that in your head. They think you can do the pH of this. What is the negative log of that? Remember, we're talking about log of 10 to the minus 1, or negative log of, right, for pH. Log means 10 to the what power will get you 10 to the minus 1. And of course, the answer is minus 1 as an exponent on 10 will get you 10 to the minus 1. But again, negative numbers screw up the general populace and a lot of students, and sometimes me. So we take the negative of the answer I just said so that we get a positive answer. So this as the H plus will get us 1. If that's the H plus molarity, to get pH, we take negative log of the H plus molarity, and that would give us pH of 1. That's pH, and this would be the H plus molarity, and that is, in fact, that. So pH is 1. pOH is 14 minus that. Are we? Well, they did it the other way. Okay. And H plus molarity times OH minus molarity will equal Kw for the temperature being stated, but it's always 25 degrees Celsius on these problems. So there's Kw. If I know if I know H plus molarity, here we go, I can divide and I get OH minus molarity. Or we could have just said 14 minus pH is POH. You're going to get the same answers, good enough anyway, either way. And we know it's 100% dissociation because that's the definition of a strong acid, but here we kind of prove it, that this much is the amount that dissociated, and we divide it by the amount that it started off with. So this is the H plus molarity, and this is the HCl molarity. And of course, it's 100%. Now, I don't recall being asked a dissociation percentage in a number and a number value, but they do think you know what it is, and they do expect that you can say, oh, this would make it go up or down or something like that, at least that. Number 2, we have a strong base, which we know will completely dissociate upon hitting water. So all the OHs come off, and I don't really care about the K so much for a pH type problem, but I was asked for the concentration of all species. So let's not just cross it off this time. All of this dissociates, which leaves none of it. That creates one of these and one of those, so that molarities of those are identical. I don't have H plus, but I do have OH minus, and so negative log of the OH minus molarity will give me POH. 14 minus that will give me pH. H plus will be the inverse log of negative value of pH. If you don't know what I mean by that, hit pause, have a think, ask your teacher. We put the negative back on before we take inverse log of it to find the molarity. Here are the molarities just from the bottom of the ice table. Technically, it's not ice, is it? Because this is final, not equilibrium. Anyway, the table. And the percent dissociation is this amount divided by that amount there. So it's 100%, of course, this time. Number 3 is a weak acid, and again, acetic acid, sort of our classic weak acid. So not all of this will dissociate. Some amount will get destroyed by going across the arrow, and then we will get an equilibrium. So this is an ice box, ICE. So some of it will get destroyed, an equal amount of this will get made, and an equal amount of that will get made, because one of these will get you one of those and one of those. So these numbers will be identical, and they will be, in this case, identical to the amount destroyed here. So this then will be the final molarity here, start minus change, and then the start here was 0, so the ending molarity of these is just X. We do products over reactants, so the power of the number in front is equal to Ka, which was stated up here. Now, if you write that in like this, you get this with the minus X part, and you end up with the quadratic formula. Now, our rule is if K is 3 decimals or more different, and I mean smaller, than the molarity is involved, and it is 4 decimals roughly smaller, then the amount that X adds to or subtracts from a molarity won't be worth considering. By the time we get done doing all the calculations and rounding off to sig figs, you won't notice the difference. So let's just forget it. And let's not subtract X, because it won't be worthwhile, and it sets up the quadratic formula. So if we can ignore this, and we can, we just get this. We're going to multiply and square root, and we get x value. So x is the value of this and the value of that. There. The value of this is 0.1 minus x. Don't forget that this value is not x, it's 0.1 minus x. The pH will be the negative log of the H plus concentration, which is x. pOH can be 14 minus that, and the OH molarity can be inverse log of negative pOH. And the dissociation amount will be the X amount, because X is the amount that moved over, right? Divided by the original molarity, and that's our percent dissociation.